All right, I'm going to put in this floor. Beams, check. Columns, check. What's this? Layout of horizontal braces, not applicable to what we're doing. Foundations, I'm going to talk about this after I do most of my steel modeling. I usually then go out to my slab layout. Again, I could go to the layout menu. You'll see that this is where we're doing most of our work. Again, this is all steel, so I'm in the steel module. If I was using concrete beams or concrete columns, I would need to have been in that module first before I'm able to install it. We were in steel, so we're able to put in steel and columns and beams. All right, back to decking, layout of the slab. You can see when I select this thing, it becomes highlighted, so to speak, or graded a little bit, darkened, so you know that it's active. And I have additional icons that appear with it. So my deck properties, my slab edges, slab openings, penetrations, and assigning the deck. So here, the first thing you need to do is select some deck properties. All right. Like I said earlier, when we were looking at the criterias in terms of tables where we can find decking and what would be automatically loaded with the program, we had some settings that showed that RAM would automatically load. I believe it was RAM deck or whatever. But that table basically is what feeds this particular tab or this dialog box in this tab. And so all these decks are loaded in by default. Uh, I usually use USD or Volcraft. Those are the wheeling is also an interesting one to do. I think wheeling were actually bought out by another manufacturer. Um, but just for now, we'll use if we were to use it. If this was a these are composite decks, by the way. This was a composite floor system, and when I say composite here, I mean a composite deck, not a composite deck and a composite beam. Um, so we'll have to put this information in here. We would have loaded in the deck and provide stud diameters, say whether or not that composite floors was short, the beams were short or unshort, and fill out the rest of this information. I'm not going to do that here because our roof deck is non-composite. So I'll just go to that non-composite tab and create a deck called roof. And for the self weight, I'll say it's about 3 PSF. The effective thickness, I'll use it. Just going to throw a number in there for now, come back and modify it later. But this basically, RAM recommends using the gauge thickness. So I'll just say, for now, something like zero point 0.3 inches or 0.181 inch. Uh, we'll give it a quarter inch. You know it's less than that. Come back to this thing later. A gauge will be less than that. So I'll just go 0.125. Poisson's ratio for steel, I believe we have zero point 0.3. Uh, elastic modulus. Here, this is where you might think that this value should be 29 times 10 to the 3 KSI, or PSI rather, but it's not. This elastic modulus value needs to be calculated. And is 29, in KSI this would be 29,000, so 29 times 10 to the 3. But if that was regular steel, it's not that. This is something that needs to be calculated based on your spacing, and really the deck that you're using and the requirements. So for now, I'm just going to put a placeholder here. Let's just call this 5,000. Okay, just to load it up. I will change it in a minute so that people out there won't say, hey, where are you getting 5,000 from? We'll explain that in another video. Just add this so that we can create our floor slab here. You know, we need to have that information loaded up. And once it's added, it can be modified later when you click change and modify the values. Now here's slab stiffness properties. This goes back into more advanced modeling in terms of making modifications to what the stiffnesses are for the non-composite floor system that we're loading up here. Um, Concrete slab. If I want it, I could just put in a concrete slab of any thickness. I'm not going to do that here, but I will label it like if it was a 6-inch slab or 4-inch slab, whatever you want it. An 8-inch slab, put in that information here, the thickness, the KSI, the unit weight for this unit weight right here calculation can be different from those that's used for the self weight. This could be for this one right here is used specifically for calculating the Young's modulus. So you have to be careful when you use this value. This one is used for self weight. I typically use the same thing just to be consistent. Poisson's ratio, um, and then the settings for your elastic modulus. Again, cracking factors that you could use or stiffness factors that you want to use uh, when you're dealing with the different slab settings and different codes. You can really modify this in a very detailed way. Some of it, you'll see just in general, we'll say, okay, these factors can be applied to bending, which means out of plane bending, vertical bending for the slab, up and down. Typical slab deflection is what we'll call it, or diaphragm uh, bending, if you will. And this is more in plane bending and flexing of the structure in the X and Y direction versus the vertical direction. These stiffness modifiers allow you to get into the detail of each one of these for flexure or for membrane. Flexure, again, is considered vertical bending, and membrane is considered in plane bending. And you would have to get into the help menu to get into the details of this orientation as far as what particular property you're modifying here. This is more advanced level, but just to let you know that your options to modify really the detail elements of the slab behavior, those options are available, but not going to be used. They're not going to be used for my particular video here. I say okay and save it. So I've created that. Now, once I've created the properties here, if I wanted to, I could assign it. Now, when I enter this deck assign mode, I'm not going to assign it here. I'm just showing it to you that it can be assigned. It has to be assigned using a deck assign mode. And you might think that's the logical next step, but it's not for RAM. Uh, However, when I enter this dialog box, I might say, wait a minute, I created a deck, but I don't see anything. Well, I created a non-composite deck, and once I click on that, I will see it. If I were in concrete, it would show what concrete elements, what concrete slabs I created, composite decks I created. So I created a non-composite deck, and that's why this has to be selected in order for the deck to appear. Is it a one-way or two-way? What's the orientation? Um, and then other things related to actually assigning it. Cancel out of this because with RAM you have to actually create the edge of slabs first before you actually lay it out. So again, the beauty of RAM is that it's very automated. So it allows you to do things in one operation, if you will, very simplified. So easy that even an architect can do it. But um, the layout here is just telling me that I'm going to have a slab edge that's going to be overhanging 12 inches left and right. This really depends if I go manually, if I go to the left as I go, as I move from point A to point B, so to speak. It's going to say, well, is your slab going to be on your left hand side or your right hand side? So I'll do this manually so you can see what this looks like. So it's on left, right? And if I go, I want the slab edge to be on the outside of our beams, all right, our perimeter. So if I go in, if you will, a left to right direction, the slab edge should pop up on my left hand side of my travel. So this is as if a person is walking from this point to that point. What's the left side? This point to that point, what's the left side? So if I went from here to here, my left side is that way. Okay, so I cancel. Also, great thing about this software is that it has an undo button, which is I think is essential. Some software companies do not have an undo button, and everything you do must be deleted and redone if necessary. That's kind of an interesting setting. They have their reasons. But most structural analysis and design programs will have an undo and a redo button. So I could, in case you make mistakes, you could erase them easily. All right, going back to the slab edge setting. Again, if this was right and I was going from there to here, it would pop up on the other side. So that's not what we want. Here, I am going to say slab edge, and it doesn't matter if I go right or left. I believe it doesn't matter, but let's set. Let's see. If I do a whole perimeter, it instantly would take care of perimeter, whether it was the left or right. Let's undo that. Come back and do it again, just to show you that this doesn't make a difference. Cancel. Doesn't make a difference, I believe. If you right click, you can easily bring up your previous dialog box. Whole perimeter doesn't. Uh, so it proves that it doesn't make a difference whether that button is selected on left or right. As long as you're doing whole perimeter, it's going to find the perimeter of the structure and draw a slab edge around it 12 inches away from the center line of the beams. All right, so apparently I saved that. Come in here and do a deck assign. Again, I am going to do my non-composite deck. It's going to be a one-way deck. That's the slab action. Here, my orientation needs to be vertical, right? Because the slab was span in between these infill beams. If for some crazy reason or another I end up doing it this way, um, the computer will show me that the direction is going this way. It wouldn't create an error or anything like that because it just basically doesn't care about how you modeled your non-composite deck. You can still run the analysis. It's just gonna be wrong because the loads will not be distributed in the correct way. So this is where the engineer must pay attention to what they're doing as far as the orientation. But there's a graphical representation here that shows you this. So let's say I was putting it in the wrong way first, and the way that we'll do it, we'll just add it to the whole floor, whole diaphragm. We'll talk about this at another time, but we'll just add it to the whole floor. You see the lines, these darker purple lines that represent the slab span. and they're going parallel to my beams here, which is obviously not what I want to do. Okay, so I could modify this, or I could undo my work. Either one works just fine. I come in here and change my orientation. Let's say change, select it. It's asking me, what do you want to change? Oh, I want to change the orientation of my non-composite deck. Now it goes the right way. Okay, so these lines represent the spanning of the deck between structural supports. All right, so I now have that deck in there. Cancel out of that. Oh, I'm sorry. Cancel out of that. Let's go ahead and run a quick data check. All appears to be well. Take a look at it in 3D. Now you see the deck showing up in addition to the frame elements we had before. X out of that. And like I said, I will be changing the property that I assigned to the deck of the elastic modulus, because for a semi-rigid diaphragm, those properties ought to be calculated. And I'll get back into it. We'll talk about semi-rigid another time. So I have another uh, model that I had before that had a more realistic calculation of the semi-rigid diaphragm, even though it might be wrong as far as the very details of it. It's not far off. We'll get into the calculation another time, but this is much more realistic as far as what it is. So we'll just go back to what I had previously with my semi-rigid diaphragm. Get into this modeler and investigate the property. This is a preview of what's to come, so to speak. So I'll investigate the property of my decking for non-composite, the roof system. I end up using 29 classic. So I cancel out of that. It's not 29. Again, I'm taking shortcuts. Go into, let's see here, stair tower. That'll work. Get into the stair tower model at the roof. Hopefully I did the right thing here. I had to have done the right thing. And take a look at the roof here. Non-composite roof. There it is. So I'll just remember these values right here. The effective thickness. This is non-composite deck, pretty much the same thing as what we have on the other model. And I'm modeling gauge is 1.5 inch most likely. Type B roof deck. Often I typically use a 20 gauge, not a 22, just because welding is a lot easier with the 20 gauge than the 22. Even though 22 is weldable, sometimes you get burnout depending on some of the settings that the welders have on their machines, and you need to use welder washers in that case. Just for the record, welder washers are recommended for decks that are really thinner than a 22 gauge. But in my experience, even 22 gauge burns out sometimes. I use a 20 gauge oftentimes. So 20 gauge, 1.5 inch type B roof deck. And you can see that my elastic modulus value here is 17,097 KSI. My effective thickness is 0.0358. All right. So let me see if I can copy that. I can remember the number, but I'll just copy it just for sake. See if it pops up in the other one. Hopefully it does. But anyway, 17,097 and 0.0358 is what's used for the effective thickness. So cancel out of that. Take a look at the structure, just you guys can see what I'm talking about here. This is a stair tower project that I'm working on, and this is the roof level, and it has, that property. Incidentally, these are concrete decks, concrete filled decks, metal decks. The stair is actually within this tower. Going back, the stairwell is within this tower right here that's braced. This is another project. Just exit out of this. Exit out of modeler here. Go back into phase one here. Go back into this here. Go back into my deck properties, composite, select this, make a modification. I remember the number as 17097, but let's see if I can right click and paste. Wow, not bad. It remembers from file to file, which is also good. So it's pasting it to the clipboard. And this is 0358. You have to click change. Just because you did this, if you click add, you're adding another deck with the same name. I'm not even sure it would allow you to do that, but change is what you need to do. So we change the properties of that. We get into the calculation of elastic modulus at another local time, but most steel roof deck manuals, product manuals, uh, will tell you how to calculate this value right here. This thickness is typically the gauge thickness. It's recommended to be the gauge thickness by RAM. That's what I use. Save the file. Now, I guess lastly, actually, I'm ready to run this analysis, if you will, at least for the gravity case. I'm not quite sure that will allow me to, but I think it allows me to get through the gravity modules. No, there are no uh, lateral members in here, so I can't get into any RAM frame or anything like that. But let's test it out and see whether or not it allows me to run gravity. You can see here in RAM Manager, the button, if you will, the traffic light of this these various modules have changed. Okay, so Modeler is giving me the green light because everything I need for gravity analysis has been done. As far as running something, I don't have any real load other than the self weight in the analysis so far. And so I have the green light to run because I have the basics of loading, geometry, member properties, with some boundary conditions. We didn't talk about boundary conditions, but we'll go and take a look at that. But there were some default boundary conditions that were set here, and that's what RAM has in terms of understanding the fixities of each point. Just so you know, gravities are pin, pin, and fixed for torsion, obviously, but they're pinned models. But I think they actually might be pinned for torsion just as well. But it doesn't matter for what we're doing. Is we don't have any eccentric loads. A real structure would not allow you to, a real analysis would not allow you to run something like that. Uh, you would have to fix at least one end for torsion. But here, Modeler allows you to get away with pin situations. Anyway, long story short is that we're good for RAM Modeler. RAM Steel Beam haven't been ran yet, so it's red lights telling me, hey, I need to do something here. You're not done with that. Same thing with column, steel column. There's no concrete in here right now, but it's a red light for that. And RAM frame is grayed out because I don't have any lateral members, so-called frame members, included into my model. Okay, so let's just run a test on RAM frame. Now, When you first do this, it says that you know, RAM steel beam will create framing tables here, and then I can do a design all automatically after framing is completed. I'm not going to design all, but if I were to select this button, it would. Okay, I say okay. So we create framing tables. Now I could just look at a typical floor. Nothing has been designed. So when I click this button right here, which is supposed to show the designs, I don't see anything. That's because I didn't run the analysis yet. Speaking of analysis, just in general, this does a first order linear elastic analysis for the gravity load cases and incidentally for the lateral load cases. We'll get into the details of it, but essentially it does a first order linear elastic analysis in order so that it can run the analysis as fast as possible. We'll talk about that later. Now, again, when you get into these modules, the right thing to do is to check what what the settings are. So here, I need to set a design code. So my steel code, I will use ASD. We'll talk about it, but you have the options to use LRFD, different versions of AISC, steel specification, the all-time favorite of the American engineering community is the ninth edition. It's because a lot of people fell in love with this edition. It's pretty good. It's one I started off just as well. Um, and a lot of engineers are still, incidentally, just married to the ninth edition. However, we're going to use the allowable strength design method, which is different than the ninth edition, which stands for allowable stress design. All right, so this is the strength design method. Other things in here are related to what we use for castellated beam code. I set everything to AST just to be on the safe side. If I end up modeling something and not really realizing that I didn't change the code for it, I get in trouble. So I set everything that I possibly can to AST. Say, okay. Here I get a warning saying that, hey, look, you made a modification. All your optimized beam designs will be cleared. That's fine with me. I didn't do anything, and that's my intent anyway. So that's fine. Now, we can get into design defaults. Talk about this a little later. But just know here, you can set rule of thumb for the maximum span to depth ratio. Those are interesting numbers. I can get into that and talk about them. Uh, these numbers in great detail. For now, we'll leave it as 0 just to see, so you can see what happens. Do you want the computer to check the unbraced length, check the unbraced length, or consider the point of inflection as bracing? Don't check for unbraced length. Uh, if you have a non-composite or pre-composite beam, which we do have, whether or not you're going to consider the deck that is perpendicular to the beam to brace the flange of that beam. Normally, the compression flange is what we're concerned about bracing. And so, do you consider the deck as bracing or not? If it's perpendicular, yes. If it's parallel, no. Or yes. What's going on with you? These are engineering decisions. You have to figure it out. I typically select bracing as perpendicular to the beam flange. Decks that are perpendicular to the beam to be bracing the deck, to be bracing the beam because it's welded oftentimes or screwed in. But I'll say about 99.9% of my career has always been welded to the beam. at those locations. So it does a pretty good job of bracing when it's perpendicular and that system is tied in. Again, and also just as a note, we're talking about the completed structure here, not the temporary structure as is being constructed. So this is analysis that's applicable to the completed structure. Any temporary bracing, shoring, sheeting that's need to be considered should be considered on an individual basis by the general contractor and subcontractors, their engineers. All right, now for composite decks, this is a calculating the effective moment of inertia. You can get into that in detail uh, by reading through commentaries and understanding what's being required here. Not applicable to our situation, it's just not applicable. Again, the help menu is there to provide you with additional assistance if needed. So here, this is all I need to. I wanted to check the brace length, and I wanted to brace the beams that have the decks framing perpendicular to them. Consider them as fully braced. Okay. Deflection criteria. We'll get into this. For non-composite or for composite, this is where you set the dead load. Do you have any limitations? Live load, do you have any limitations? Yes, L over 360. I know this is a one story, this is a roof. We can use a different value if desired, depending on the ceiling type that we're finishing, that we're supporting. Um, and we are not going to make any modifications here. L over 360 is fine. The total net dead load of L over 240, that's fine just as well. Modifying these will change the member sizes because these are serviceability limit states. And in order for your design to be complete, you have to meet both service and strength limit states, and change one and will affect the size of the other oftentimes. Well, it will affect the final beam size. So for the most part, we'll just leave this as is, but oftentimes you'll find that deflection controls over strength in most cases, as far as limit states are concerned, or gravity, that is. So, okay. You can get into whether or not you want to camber or not camber your composite. I could say don't camber anything, which is what I'll do here for my non-composite beams. It's telling me to clear all sizes. Fine. Stud criteria. This is for composite design, not applicable for this video. I'll talk about it at another time. Web openings. If you wanted to create web openings and beams, that would affect the behavior of the beam. And also joist criteria. If we had joists in here, uh, we could have all of the design settings, general design settings for joists set within this dialog box. Nothing needs to change here. We don't have joists in this model. We could assign the deflection criteria separately. We could assign beam sizes that we want to use, user choices. Here on the process is where we can actually start our design work, view our design work, see other information related to designs. And under reports is self-explanatory. We can pull reports for our analysis and our design. RAM actually lets you do vibration checks and vibration analysis here. I typically control vibration through my deflection criteria, so I oftentimes never get into the vibration menu. View allows you to see things as you would like to, in terms of I might show beam sizes, any type of restrictions I have on them, show all my non-composite beams. You see they were highlighted as I clicked on this to show the composites. Everything turned off. User assigns, nothing happens. Custom design, nothing happens. I could just say, get X out of this, and I should be fine. Oh, don't let me X out. Go to default, none. Now I can say, okay, you got to be careful about this show option because you might end up with um, some type of annotations that are stuck on your screen and you're wondering how to get rid of them. Oftentimes it's based on your view menu and some defaults that you have selected. So none is preferable here. So okay. All right, enough of the talking. Let's run the analysis. Design all. And there. Gave you a whole bunch of beam designs, infills, self-weight, W8 by 10s. Uh, the interiors are W10 by 12s. Of course, we all know that, for constructability reasons, we will not use these member sizes just because they're so small. Uh, as far as they're really flimsy, you're not going to have a beam that's 10 inches deep spanning 30 feet. It would not be easy to construct that beam. It would be deforming very easily just during the fabrication process. So those are not typical sections that we use, but based on the strength analysis, this is what is required. Okay. So here, another thing is that you can select just like your code to try to see, okay, as far as the design strength ratios, you know, which one is being over, which ones are stressed out the most. Is this thing behaving like I would expect it to behave? Where the interiors that carry more load um, probably will be stressed out more than the ones on the perimeter. And the ones on the perimeters that are girders will be more stressed out than the ones that are infills, all right? That's carrying only floor slab directly. And that's what this color coded uh, screen view is showing us here. So the beams are colored according to their stress ratio. This is the color scale. Now, I might want to actually see the number. I click on show values. Okay. And then it shows me what's controlling. Here, D is deflection. All right. So that ends up controlling. Like I said, oftentimes that's the case. But we can see that on the perimeter, we have the stressed out just based on deflection, if you will, allowable deflection. And we have about 70% of the capacity being used. Here, 71% of the capacity being used. Here on the perimeter, we expect this one right here to be the same as this one. It is. It actually would be the same as any one of these. They're the same tributary area, same length, all things being equal. All these right here on the interior will be the same. On the perimeter, it's different. And there you have it. You see the stress ratios. So let's close this file. We'll get into this a little bit more in the future. Um, let's do something real slick. Let me change my deflection criteria to, if you will, my design criteria to just, let's just say I want a minimum depth. I typically like to use something as as far as for every foot of span, I would recommend having at least, uh, I would say at least, zero point 0.7 inches, if you will, all right, almost 3/4 of an inch for every foot of span. You can go, you can go lower than that. go to 0.6. I mean, you could go much lower and it still works. So that number that I will calculate, let's say I'm using zero point 0.7 here uh, in terms of the depth that I need. So I want 7.7 inches for every foot. Okay, this ratio right here is set in feet per feet as far as the span over the depth ratio is concerned. But my depth is normally in inches, not in feet. So in order to do a quick calculation, just to make sure that I'm right here. So I'll just set a number like 1 over zero point 0.7 as far as this ratio is concerned. Hold on, 1 divided by 0.07. Uh, uh, 1 over zero point 0.7. That 0.7 times 12. So take the ratio that you want as far as the depth of the beams. If it's zero point 0.7 inches, take that number and take 1 and divide it into that number, or take the inverse ratio of that. So 0.7 inches, 1 over 0.7 inches. That would give you 1.428 or 1.43. Multiply that number by 12 to convert it into feet, and I will have 17.14. So I'll say 17.14, but 0.14 is not really a good number. I typically use round numbers, but just for example's sake, I'll take it as 0.14, so we can see how close this thing actually gets. And once I do this, it should tell me that it's going to clear all of my designs and rerun the analysis. Beam sizes will change. All right. So there you have it. It's telling me that it's changing all my optimized values. Okay, run the analysis again, and now you see my 8s have gone up to 24s, which makes sense. And it's choosing the lightest 24 it could possibly choose here to meet my deflection criteria, 24 by 55. So something that's spanning 30 inches, 30 feet, take that and multiply it by zero point 0.7, I actually should get like a 21. But it gave me a 24 by 55. Let's investigate why. We'll get into greater detail, but let's see if it's saying deflection is controlling them. It's not. It's saying it's being controlled by the interaction of the loads at this location, not deflection. But it sized it first based on deflection, and then it checked it for strength so that it meets that criterion. So all of a sudden, all these things are now controlled by load instead of by strength instead of deflection. We can investigate it in detail by going to cancel, by going to basically process, view, or update, and then we get this crosshair and we select one beam, and then we could take a view of the results and we can see what's controlling. Here's the moments that are in the beam. Here's the deflection value. So deflection is not an issue at all here, and the strength that's controlling. All right, so that's what you do in order so that you can change the minimum depth of this from the beginning. let's say I was to use another value, a higher value here that would represent more stiffness. I want 24, for example, which should give me an inch per foot here. I run the analysis, and now I have an inch per foot. Okay, I'm sorry, a half inch per foot. It's a half inch per foot when I put in the 24. Inch per foot would be 12. All right, so it's a half inch per foot. So now I know this is 30 feet. I can look at this and say, oh, 16, that works, right? I know this is 25 feet, which is, half of that is 12.5 inches. Well, it's going to pick a 14, right? We don't have W13s. Now take a look at this thing in terms of what's controlling this deflection, all right? So the key observation here, the key point is that this span to depth limit can grossly control the selected size of your beams. All right, so be careful when you have this information checked out here. Uh, like I said, depending on where you're at, you might have your values that you like to use. Some people use a value between 20 and 24. I believe that's what's recommended by RAM. And if I use the value of 20, then let's see here. That's 20 corresponds. Hold on. 20 divided by 12. Let's see. So that's like 20 is about 0.6 inches per foot, which isn't a bad number either. All right. Okay. But like I said, I like 17. That's a little bit stiff. We'll go in between this thing, split the difference, and I'll just say we'll use 18 for now. Splitting the difference actually would be 18.5. Those are good sizes. Preliminary. That's chosen by the computer. But anyway, I know that my deflection criteria sets that. So let's come in here. Let's put a little load on the structure because we didn't get to do that the first time. So all that analysis is based on the self-weighted structure. Here I will show you, this is the tab that we use to put loads in, or you can go to Layout and RAM Modeler, Loads. You put a load in. Here I'm going to put in a uniform surface load, call it roof. Can't get too elaborate with the names. I think there's a character limit to the number of characters if you can't put it in there, but it's not limited so that you won't have something that's understandable. So I could just say roof loads. In fact, I could say uniform, maybe roof loads. For dead load, I say 25 PSF. For line flow, I say 30 PSF. I'll make it unreducible here just to be on the safe side. Make sure that nothing changes. As far as the mass load, this goes into the weight and earthquake calculations. I'll add additional 25 PSF so it could add more, that loading to our dead load calculations for earthquake weight of earthquake. It's telling me right here what's the current self weight criteria, and what I have for storing masses. And the other settings that I had in the beginning was showing you we were using roof loads versus snow loads. So here, all these settings are fine. If I wanted to add a construction bed load and live load, I can. This is applicable mainly to non-composite design, to composite design. I'm not going to add any information here for my construction loads. So I add it. So, okay. Now I need to assign it or lay it out, as Ram would say. So these loads will be laid out on the structure. Once I select that button, I get this surface load layout mode dialog box. I select the load that is shown there, clicking on the label. I can add it to the whole floor, or I can add it in individual locations. Let's do an individual location thing first so you can see that it can be added locally. What if I do something crazy with my polygon, like this, 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 and this? Get a warning. A polygon is not a polygon, so it needs to close. All right, so it's okay. So I come over here, I can do that. Either which way, though, you can add kind of like a little bit of variations as far as you don't need to go in 90-degree orientations. So things can be at an angle. So it's okay. Um, I could undo that, but I don't know what's been undone. I could just undo it some more just to be on the safe side. I come over here and I still don't know whether or not it's been undone because the loads are not shown graphically. So here I have to select the loads and say show loads, and it shows the first one. I clicked on the undo button 2 times, so the last two area loads went away, but not the beginning. I could click on the load, that hatch pattern, and it gives me information regarding what is that loading. Same settings as what was found in the properties dialog box. Close it. Now here I go back and I say I got to get rid of this load because I really want it all over. So I can delete a single load area by selecting the delete button and clicking on it. Now I want to apply it to the entire floor. So with the load selected, if I hit whole floor, it gets applied from slab edge to slab edge. And that's what I want to do. Say okay. Now I have a total load of 55 PSF on this thing plus the self weight of the deck load on this and the beams, the structure, and etc. Now I can hit the escape key and nothing happens, but I want to reset this because this is kind of just showing me my hatch load area, and I want to now find out some information about the beams themselves, particularly their boundary conditions, their fixities at the columns. But I can't get rid of this thing. So how do I get rid of this thing? This is where I kind of end up poking around and try to figure out how to get rid of this thing. So right click and I say cancel, and it gets rid of it. Usually when you can't get rid of something, it's because you're in the command and you need to right click and cancel out of the command or somehow break out of the command. Right click and cancel usually does the trick. So like I said, I want to check out the fixities of this beam. Really, that's kind of this button right here. Or I can go to layout beams and see fixities, find out what we have. This is okay, so this is to assign the fixities. We'll get back to this dialog box, but it tells you basically I could apply my whether it's fixed or it's pin, which are your only two options to the major axis and the minor axis left and right of the beam. But how about viewing what's already there? I go to the options menu, show fixities, show all of them. See, nothing pops up because these are gravity beams and they're already assumed to be pin. If I was to change one of these beams, let's do the same thing for columns before I change one of those beams. So I could take a look at this in elevation. Let's take a look at the elevation of this line, that one line. Okay. No frame, beam, or wall has been selected. In order to take a look at the elevation, apparently you need to make some frame, columns, or beams. You have to have frame elements, which is an interesting thing because I guess it considers you're not interested in it. Let's see if we could take a back door, go in and through the 3D, and then turn to frame elevation. Try to see if we could backdoor our way into it. We can't. All right, so it's consistent within that aspect. All right, so we have to define frame, columns, or beams in order to take a look at the elevation. So I'll just, this has a hair in it that tells me that I'm under a command. When I change, I hit the escape key and change back to my pointer and with the arrow, so I know I've exited the command that I was in. Here I can change the properties of this beam from gravity to lateral. I'll change this one, this one, this one, and this one. Automatically, you see my gravity beams have been changed to lateral beams, and there I get a O's and X's at the ends of the beams, left and right, up and down. These O's and X's represents pinned or fixed settings for that beam. As I said before, um, I was under the impression that it would be pin, 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 uh, by mistakenly, if you will, for RAM structural system, but it knows better and it does pin, pin, fix, fix for torsion. So the first letter represents the major axis, then the minor axis, then the torsion at that end. So pin in the major, pin in the minor, fixed for torsion at the left hand side. That's what that represents. Now let's see if that allows us now to go into the elevation and take a look at these columns. It does, but it only shows the beams in elevation. It doesn't show any columns because we don't have any gravity columns. Now I can exit out of that. Let's change some of these columns to to lateral. In order to do that, I have to select column layout and then make these modifications here and change from properties from being uh, gravity to lateral. Everything else that is not selected is not applicable. These are the only things that will be modified here, the properties. So I'll fence it in, fence in these 8 columns, change them all, right click, cancel, set, and take a quick look at the elevations of these things. And I should now see the fixities that are assigned just as well. So by default, the columns are fixed in all axes, major, minor, and torsion, top and bottom. You can change that based on your model, but um, by default, they're fixed. So these are the default settings for this thing. Let's get back into our plan view. and do a quick data check. We'll just do gravity only. If we were to do frame, we're going to have a problem because this, you have to assign member properties as part of the modeling process for so-called frame elements. So you have to have a preliminary size assigned to it. Here I did not do that as a user for the columns or the beams. So I should see at the very least, I would imagine I will get 8 warnings for the column, 2, 4, 6, 8 for each one of them that are frame columns. They don't have member properties assigned. And possibly an additional 4 for the beams because they don't have user assigned members, but they might have been able to have their the size that was selected from RAM being assigned to it by default just as well. But typically you would get errors for these if you don't have user assigned properties for them. So select and there you go. I have 8 and they're all for the columns. That's because by default the beams were assigned from RAM beam. Those sizes were assigned to those frame beams. And it's telling me in the warning list that, hey, look, I don't have a member size assigned on this story. It's called first story. And then it tells you the location where the issue was detected and what action needs to be taken in order so that you can get rid of this error. So it says assign a size for this column, either in modeler or in a design module, another design module. So just to make sure you see the beam sizes, you say, hey, look, I didn't really pick a beam size as manually, but apparently I have a bunch of beam sizes assigned to this now. What are they? I click on W12. Well, I'm sorry, yeah, this W12 icon, so to speak, just shows the sizes of the beam for all of the lateral frames. Now let's just go ahead and select some sizes for the column so we can see how to get rid of this error. Here's where we assign sizes using this icon, so-called W12, which is also found from the layout column. Come here and it tells you what the icons means, assign the size. These are 15 feet high columns, so I will just select something like a W. I like to use 14 for something this high, and I would say a good rule of thumb for these type of columns as far as the unbraced length is concerned and the size of the beam that you use. Here is where an inch per foot will serve you very well, or close to an inch per foot will serve you very well. So we'll use something like a 14 by 90, which is a typical column size for this area. It can be taken down once we run the analysis and we find out what the stress ratios are or the strength ratios are, the behavior of the structure. We might decide to optimize it a little bit more, but this is a very good rule of thumb as far as any preliminary analysis is concerned, and oftentimes this will be the section that you use for your final design. So 14 by 90, let's go ahead and assign it to these columns. I don't see anything happening. I could select everything, and I don't know if anything is happening, but it's happening. Save the file. And how do I find out whether or not it's been properly assigned? Well, it's a column, so I have to go in elevation, and I'll see my 14 by 90s. I could decrease the size of this thing to make it more legible, if you will, and you can see where these things, where the properties are assigned. You can go really small or really big if you ever have an issue. This is the way you control the graphics on the screen. Exit out of that. Let's go ahead and run a data check. Frame is good. Gravity was good. I can do it integrated. Everything is good. I can say exit out of that. Now you can see RAM frame telling me that I'm active, and you can start filling out your lateral design criteria in the RAM frame section. But it's best to complete this section here on the left hand side first, uh, because you need to, it's best idea is to go ahead and run the gravity analysis before you get into the lateral analysis. It's a back and forth thing, but as far as a sequence is concerned, you basically have to have your gravity analysis ran before you can actually get a green light on your RAM frame analysis. So I'll just go ahead and run this. Everything's ran. It's running. It's going through the process of figuring out things. When the circle is disappeared, it's complete. I can select my layout, and then I can take a look at my sizes. These are all the design sizes. Take a look at the ratios, what's controlling it. There you go. These sizes are optimized pretty much. Take a look at my controlling values. This is right there where it needs to be. So I exit out of this column. RAM column is a whole different story. Not difficult or anything like that, but I'm not going to go into it right now other than to say just a simple thing. I will select a design code for the column and the base plate. It's telling me it clears the design, and I'll just run a quick analysis of it just so I can get a green light, show the values, these columns that have been set. Well, what are the column sizes? I have no idea. So can I just view the column sizes from here? I think you can, but the way that I typically see my column sizes at this point in time is by actually selecting view update, or you can go to the process menu and go view update and select a column. And then I get a table that pops up and it tells me this is column line A3. This is the size that has been selected. These are the trial sizes that are available. This is what you came up with. That's just as well. We could take a look at the results. Self-explanatory, like I said, gravity column design only. We can select another size and analyze it. We'll get into that another point in time. But it's possible to select another size and also run the analysis on it and see how it behaves. Uh, we'll do that at a later point in time. But just so I can get a green light on this, I had to run that analysis, and I'll just go ahead and exit out of RAM column now, and I should get a green light. We'll pause the tutorial at this point in time so that we could get into further discussion into the RAM cases. It's kind of on a fresh basis. That's it.